Hi guys, thanks for tuning in. In this video, I'm going to talk about vector fields acting upon curves. This will be my last video for this chapter. So for our first example, we're going to see how this vector field that we saw in our previous video acts upon this curve, an ellipse centered at the point -4, 2. Now what I want to stress for this example is that the ellipse and the vector field are two mathematically distinct objects. They're not related to each other in any way going into the problem. The ellipse is not a trajectory for this vector field. You can tell because you don't see any sort of tangent relationship between the field vectors and the curve. If you pick out a couple field vectors, you'll notice that they are not tangent to the curve. So it's not a trajectory. And I didn't generate this ellipse using the vector field in any way. I came up with both equations completely separately. And I'm going to see how the vector field acts upon this unique independent object that I came up with by plotting that ellipse. So what you'll see on the screen right here is just a reminder of what I just said. The blue vector field and the red curve are not related to each other. Now the way to imagine this problem is you want to imagine that your vector field is a set of ocean currents under the water. And you want to imagine that your curve is like a set of train tracks that you built under the water. Maybe you're some sort of eccentric billionaire and you're building a train or a monorail or something under the water. And when you build that train underwater, in addition to making it watertight so that the train doesn't flood, you also want to make sure that the train doesn't get derailed, and you want to know how the ocean currents are going to act upon your train as it's traveling along its route. So continuing with our example, we don't really need to plot the entire vector field to understand how the ocean current is going to affect our train. Instead, we just care about the vectors whose tails are on the ellipse. The idea here is if you want to know how this ocean current is going to affect your train as it loops around its track, you really just care about what the ocean is doing near the train. So let's say you're building your little monorail loop under the water off the coast of New York. Well, you don't really need to know what's happening with the ocean all the way over in Tokyo. You just want to know what's happening in the ocean by your train. You need to know about the actual train currents that are hitting your train as it moves around its loop. And mathematically, the way we do that is we take our m of xy and our n of xy, and we plug in x of t, y of t. So we look at a plot of m of x of t, y of t, comma n of x of t, y of t. And that will limit our plot to just the field vectors whose tails are on our ellipse. And then we could start to ask ourselves, hey, what would we experience if we were on this train going in a loop around this elliptical track? How does this first mathematical object, our vector field, act upon our curve, our train track? And you can see the first picture that we have right here is pretty straightforward. If you look at the field vector and compare it to the tangent vector for our train, it looks like the wind is at our back, right? To mix metaphors here. Basically, the ocean current is pushing in the same direction as our tangent vector, meaning that we're getting a little boost from the ocean current there. It's kind of speeding us up as we're going around the track. And we could continue this analysis as we take a full loop around our track. And maybe I'll just pick out a couple interesting points where we could talk about what's happening. So here's another one that's interesting. Looks like roughly, I didn't do it perfectly, but I was going for the tangent vector and the field vector pointing in roughly the same direction. So again, another instance of the wind being at our back. It's kind of like if you've ever been riding your bike on a windy day and you're pedaling and the wind is at your back and you feel like you're just the best bicyclist ever because that wind is really speeding you up as you go. You have a force pushing with your tangent vector and speeding you up as you go. In contrast, we have something more interesting going on here. So I could plot our tangent vector, and you could see that there's an obtuse angle between our tangent vector and our field vector. So overall, we would say that that field vector is probably trying to slow us down. But in this case, it's not actually as interesting looking at the angle between our tangent vector and the field vector. What's more interesting actually is looking at the angle between our normal vector and the field vector. And right here we see an acute angle. So basically it looks like this field vector is kind of pointing with our normal vector for the most part. And how would you experience that? Well, if you've ever driven on a highway on a really windy day, particularly if you're in like kind of a rural area with a lot of cornfields, if you end up going to a university where you have to drive pretty far through some rural areas to get there, you'll experience this while you're driving to your campus. A lot of times the wind is kind of whipping across the highway, kind of perpendicular to the highway. And when a huge gust of wind hits your car, you'll really feel it in the steering wheel. It's almost like the wind is trying to derail you, trying to push you off the road. And that's what's happening right here, is we're noticing that this field vector is really giving us a strong push in the direction of our normal vector. Basically, this field vector is trying to change our direction. It's not speeding us up or slowing us down as much as it's trying to change our direction, trying to blow us off of the curve, trying to derail the train off of the track. Let's look at a couple other points and we'll continue with this sort of analysis. So at this point, looking at our normal vector is not very interesting, but looking at our tangent vector versus our field vector is somewhat interesting because it looks like they're pointing in opposite directions. And so the example here is we have our field vector pointing against the direction of our tangent vector. And again, I'm going to go back to the example of riding your bike. If you've ever ridden your bike on a really windy day and you're riding into the wind, that's not a very pleasant experience because you're pedaling and pedaling and pedaling, but it feels like you're not getting anywhere because the wind is just blowing in your face. And no matter how much you pedal, that force is trying to slow you down. And so what you might have noticed in that analysis is that I was really talking about how these field vectors can be broken down into their tangent component and into their normal component. Basically, is the field vector pushing with or against my tangent vector as I'm going around the train track? And is the field vector pushing with or against my normal vector as I'm going around the train track? I'm breaking down my field vectors into their tangent and normal components. The tangent vector, or a force with or against the direction of the tangent vector, is going to be what we're going to notice is like speeding us up or slowing us down, right? So a force that's, if the wind is at our back, we're thinking about that as like speeding us up because the wind is with the tangent vector or the water current is with the tangent vector. And then if we're talking about the normal vector, we're thinking about the force trying to change our direction. So we kind of get two pieces of information out of every field vector. Is that field vector speeding us up or slowing us down? And is that field vector trying to change our direction? Maybe it's trying to push us into the middle of the track. Maybe it's trying to derail us off the track. But either way, we could try to figure out how our field vector is attempting to change our direction, essentially. All right, so let's look right here. Breaking down field vectors into two components. So let's formalize this idea. So we could look at the push of the field vector in the direction of the tangent vector. And honestly, I'm just taking the formula that you guys learned earlier this year, the push of a vector in the direction of another. And we can also look at the push of the field vector in the direction of the normal vector. And again, it's the same formula from earlier in the course. I'm just looking at how the field vector is acting on tangent vectors and how the field vectors are acting on our normal vectors. So, it's just that same old formula of x dot y over y dot y times y, the push of vector x in the direction of y. But in this case, our vector is either the tangent vector or the normal vector. And this is going to become such a big idea in this course that we actually associate a phrase to these formulas. The first formula for the push of the field vector in the direction of the tangent vector, we call that the flow of the vector field along the curve. And then for the normal vector, we call it the flow of the vector field across the curve. A couple things to notice here. One is that we're using the right-footed normal vector here. Y prime of t comma negative x prime of t. We're not using the main unit normal. The main unit normal would not be a great choice for this chapter because the main unit normal is always switching sides based on the concavity of the curve, right? It's always pushing into the change of direction. We want a much more consistent reference point, and the right-footed normal vector is a great consistent reference point because it's always pointing to the right relative to our tangent vector. All right, so let's see how we would actually use this to solve some problems. What I love about this chapter is it's going to be a little bit lighter on calculation and a little bit heavier on visual analysis, visual inspection. So let's continue with the same vector field and the same ellipse. And we're going to plot these vectors that we just defined. We're going to plot the push of the field vectors in the direction of the tangent vector. We're breaking down our field vectors into tangent and normal components. Let's look at the tangent components. What we're doing here is we're limiting our field vectors to merely how they're affecting us, our direction of motion, tangent to our trajectory. So basically, we're just looking at, are these gusts of wind, or are these ocean currents, are they speeding us up, or are they slowing us down? Is the wind more at our back, or is the wind more in our face? And you could see, if you compare the direction of the tangent vectors with these, with the push of the field vectors in the direction of the tangent vectors, when they're pointing in the same direction, we're getting a little boost. And when they're pointing in opposite directions, we're getting slowed, the wind is trying to slow us down a little bit. And then when these vectors have a larger magnitude, that effect is exaggerated, right? The larger the magnitude, the stronger that push. We're thinking of these field vectors as a force, and a force is a vector quantity, right? It has a direction and magnitude. So we see the direction on the screen, and then the length of that vector is representing the magnitude. How strongly is that effect happening? Now, we could try to draw a conclusion here as well. We could try to determine whether the net flow of the vector field along this curve is clockwise or counterclockwise, and we do that through visual inspection. We look at this plot, and we basically just try to look at these blue vectors and decide, does it look like the net flow of this vector field along the curve is clockwise or counterclockwise? Is it with or against my tangent vectors? And in this case, just through visual inspection, we say that the net flow of the vector field along the curve is clockwise. Now I'm going to offer some advice here. You guys want to get very good at this sentence. The net flow of the vector field along the curve is clockwise. The way that I wrote this sentence, it's very clear that we have one object, a vector field, acting upon another, right? So please don't write things like it is clockwise. That's a common thing for students to try, and that's a great way to have to go back to the drawing board on your try it problems. Because if you just write it is clockwise, well, what is clockwise? What does it stand for? And it completely erases the idea that there is one mathematical object acting upon another mathematical object. The net flow of the vector field along the curve is clockwise. And at this moment in time, we're able to do that just through visual inspection. Honestly, let's be clear about what you're doing here. You're kind of integrating using your eyes, right? You're accumulating. You're looking at the accumulation of some vectors visually. And next chapter will be all about formalizing this and talking about how to use the actual tool of accumulation that we have in a calculus course, which would be an integral. So we'll get to that next chapter. This chapter, we're not really going to integrate. We're going to do this visually. We're going to inspect these plots. And you can kind of see it. Essentially what's happening here is it looks like these clockwise vectors, particularly based on their magnitudes, are overpowering the other vectors that we see. So yes, we do have we have a bunch of clockwise vectors here. Those are overpowering what we see going on in the other direction. So kind of just a visual analysis. All right, and we could do the same thing with the push of the field vectors in the direction of the normal vectors, and we can kind of get a sense of how these field vectors are trying to change our direction. Is the net flow of the vector field across the curve inside to outside or outside to inside? So very similar setup here. This is the push of the field vectors in the direction of our right-footed normal vectors. And you kind of just have to ask yourself, now this all works, by the way, because cosine comma sine has a counterclockwise orientation. And because cosine comma sine has a counterclockwise orientation, this means my right-footed normal vectors are going to be pointing outside, right? These are going to be pointing inside to outside. Our right-footed normal vectors point inside to outside when we have a counterclockwise parameterization. And then our job is to look at these blue vectors and ask ourselves, are these blue vectors pointing with, on the whole, in the aggregate, does it look like these blue vectors are pointing more with our normal vectors or more against our normal vectors? And then that'll help us determine if the net flow across is inside to outside or outside to inside. And in this case, it looks to me like the vectors that are pointing inside to outside are going to overpower the vectors that are pointing outside to inside. So in the aggregate, it looks to me like the net flow of the vector field across the curve is inside to outside. And again, this is a phrase that you want to get very familiar with because there's going to be a lot of try-it problems that end with a sentence like this. Or you maybe start with it as, the net flow of the vector field across the curve is inside to outside, and then it's because it's a try-it problem. Then you would say the word because, and you'd explain why you think that's happening. So just use that as like a basis for the next step of your solution, which is this is happening because whatever. All right, so moving on. I can kind of summarize all of this just on a nice slide here where you can see all of the material at once. So we have two different situations, the net flow of the vector field along the curve and the net flow of the vector field across the curve. And it's really just the push of the field vectors in the direction of the tangent vector and the push of the field vectors in the direction of the right-footed normal vector. And we really have three situations. We could end up with the net flow being clockwise. The net flow of the vector field across the curve or along the curve could be counterclockwise. The net flow of the vector field across the curve could be inside to outside or outside to inside. And in both scenarios, it is possible actually to have a perfect balance between the two different sets of vectors. Clockwise and counterclockwise can balance out to make zero. Same thing with outside to inside and inside to outside. If you get a nice enough balance, it is possible to conclude that the net flow across is zero. Now, in terms of what vocabulary you guys should be familiar with from a more traditional calculus class, if you Google the net flow of a vector field across a curve, you're probably going to find my website or a U of I related website, because this terminology, you really only see this in this U of I course. It's a colloquial way of describing a physics term that you might be familiar with, flux. So when you guys leave this class, if you ever hear about the net flow of a vector field across a curve, the language that will probably be used is the word flux. And the net flow of a vector field along a curve, the physics idea that you typically see is work. Because think about what work is. Work is a force carried across a distance. And that's kind of what we're going to end up doing, especially as we get to next chapter and we get to start integrating. We start accumulating using an integral. Well, if you accumulate a force across a distance, in this case an ellipse, well, accumulating that force across that distance, we're going to call that work. So you guys will see in later chapters as we start integrating these quantities, we'll get a nice connection to your Physics C course if you happen to be taking Physics C. And then finally, I'll post these to Schoology for you guys, but I have a couple of Wolfram demonstrations that if you download the free Wolfram player, you can kind of play with an example that's very, very similar to the stuff I was showing you, but you can drag a slider and really see what's happening at each point. So we could follow our tangent vectors as we progress along a curve, and then we could look at the normal and the tangent components of the field vectors and then see what's happening as we go along that curve. So feel free to go to demonstrations.wolfram.com and look at the demo called Vector Field Acting on a Curve. Or you could go on Schoology, and I have my own version that I've created for you guys where I just changed the equations to match with the example that I was showing you. And as you play with that Wolfram demo, if you do choose to download the free Wolfram player and you do download this demonstration to experiment with it, you guys can change the vector field. And I believe you're able to change the curve as well. And then as you drag this slider, you're imagining that this train is going around the train track. And at each point, you can look at the tangent vector and you can look at the tangent and normal components of the field vectors and see basically how that vector field is acting upon that curve. All right, guys, thanks for tuning in. Have a great day, and make sure that you have also seen part 1 and part 2 of my lecture for this chapter. Have a great day.